Welcome to 6G6Z3003 Dynamical Systems and Chaos. As you can see, the first topic we're going to look at is separable differential equations. So this is chapter 8 from the book entitled Differential Equations. The aims and objectives: we're going to review basic methods for solving some differential equations. We'll apply the theory to simple models, in particular chemical kinetics, population modelling and electric circuits. I'm going to introduce you to existence and uniqueness theorems. We'll just understand these, we won't go into all of the analysis, and we're going to interpret the solutions in physical terms. So the first type of differential equation we're going to look at are simple separable differential equations. So we'll illustrate this with a simple example. So if you look on the left screen here, we have dy by dx is minus x over y. So if you think about it, we're given the derivative and we'd like to find a solution y as a function of x. You'll know by now that the opposite of differentiation is integration. So we're going to separate out the variables. So if we multiply both sides by y, you'll see we get y dy by dx is equal to minus x. So we've separated out the variables. Next, we're going to integrate both sides with respect to x. Okay, so we integrate the left-hand side with respect to x, and we integrate the right-hand side with respect to x. And now on the left-hand side, you can see we've got a change of variable of the integral. So we can just, in effect, cancel the dx's. So we'll have the integral of y dy is equal to minus the integral of x dx. Again, this is just A-level standard integration. So remember, to integrate polynomials, we add 1 to the power and divide by the power. We have a constant on the left-hand side, and this is minus x squared over 2, and we'll have a constant on the right-hand side. Okay, but from now on, when we do questions of this form, we'll assume there's one constant. So we can write this as y squared over 2 plus x squared over 2 is equal to some other constant, let's call it c. And then if we multiply through by 2, we can end up with a final answer that x squared plus y squared is equal to 2c, but we'll call 2c r squared. So this represents the solution to the separable differential equation. Now the question is, what do these solution curves look like? Okay, so here is our differential equation. Dy by dx is minus x over y. We've just solved it to obtain x squared plus y squared equals r squared. And I'm sure you know for different values of r, we get circles. So these are called the solution curves. And you'll see here that when x is 1 and y is 1, then dy by dx is equal to minus 1. So the gradient at that point was minus 1. Okay, so that is our first example. The next example we're going to look at is another separable ordinary differential equation. That's number 2. So we're going to now consider dy by dx is equal to y divided by 2x. So again, you can see it's a simple separable differential equation. So again, we separate out the variables. So in this case, we are going to multiply through by 2x. So we'll get 2x dy by dx. Sorry, no, we don't do that. We want the x's and y's to be on the correct side. So in this case, we have to divide both sides by y. Divide both sides by y. And we'll leave the 1 over 2x. And we'll also make it easier if we put 2 in the numerator. So now we integrate both sides with respect to x. So we'll have 2 times the integral 1 over y dy dx, and we can change the variable of integration on the left hand side, and this is the integral of 1 over x dx. So we've separated out the variables, so we're going to integrate with respect to y on the left, integrate with respect to y on the left, and integrate with respect to x on the right. So this will give us twice the integral of 1 over y dy, and if you remember from A level again, the integral of 1 over y will give us a log mod y. Okay, plus a constant, but we'll collect the constants over on the right hand side. So on the right hand side again we have log mod x, and then we have our constant. So we've combined both constants and put them on the right hand side. And if you remember your laws of logarithms, 2 log y can be written as log mod y squared, so the 2 goes into the power, and c we can write as log of a constant, and log x plus log of a constant will give us, so this will give us log c mod say k, so we're going to let k be log c. And then if you take exponentials of both sides, we end up with a final solution that mod y squared is k mod x. So here is the solution for this separable differential equation. Now again, we need to know, what do these solution curves look like? Okay, so here we have our separable differential equation. dy by dx is y over 2x. We've just found the solution is y squared is k mod x. And if you think about it, these give you parabola or parabolae. So y squared is x, gives us a parabola, but on the xy axis rather than the y-x axis. And in this case, you can see that when x is 1 and y is 1, then dy by dx at that point is 1/2. And we can also find dy by dx at other points on these curves. And notice we've plotted y squared equals k times x to get the curves on the right of the y-axis, but we've also got y squared equals minus k times x on the left-hand side. So remember, k could be positive or negative, and notice that there are an infinite number of solution curves in this case. Okay, the final example we're going to look at for these separable ODEs. So number 3, we're going to look at the separable differential equation dy by dx is equal to minus y over x. So again, we separate out the variables, we collect the y's on the left hand side, and we leave the x's where they are. Next, we integrate both sides with respect to x. So I'll have the integral of 1 over y dy by dx dx, and we change the variable of integration is minus the integral of 1 over x dx. So on the left hand side, the integral of 1 over y dy is simply log mod y, and this is equal to minus log mod x, and then plus our constant. So remember, again, we combine the constants and we end up with one constant. So log mod y is equal to minus log mod x plus, say, log k. Okay, so c is equal to log k. So log mod y, again just using properties of logs, this will give us log of k divided by mod x. And then again, if we take exponentials of both sides, okay, because exponentials and logs are opposite functions of each other, then we end up with the final solution that mod y equals k divided by mod x. Okay, y equals k over mod x. So for example, if k is 1, then it's a bit like y equals 1 over x. So again, the question is, what do these solution curves look like? So in this case, we have dy by dx is minus y over x. Again, we found the solution mod y is k over mod x. And I've just drawn a few solution curves here. You can see they are hyperbole. Again, when x is 1 and y is 1, you can see that we get dy by dx is equal to minus 1. So this is a way to find the solution curves for these separable differential equations, and we will come back to these solution curves later when we look at linear differential equations. And our final example is going to be an example for final example is a population model. So here is a separable differential equation, and this is in the notes. So we have dp by dt. So I'll just show you the notes for the separable differential equation. This is example 3 in the notes. So this is example 3 in the notes on page 3. Okay, so we have dp by dt is equal to p times beta minus delta p. And this model is used to model population of fish in a large lake. So P is the population of fish. Let's draw a little fish. That's not a very good fish. Let's draw a proper little fish. Okay, so this population of fish in a lake. Beta is related to birth rate of fish, and delta is related to the death rate of the fish. Okay, so again, this is a separable differential equation. So if you divide by p times beta minus delta p, then on the left we'll get the integral of 1 over p times beta minus delta p dp. And again, changing the variables of integration, and this will equal the integral of 1 dt. Now on the left hand side, again, if you think back to A level, the way we can do this integral is we can integrate by splitting this into partial fractions. Okay, you can integrate this by separating it into partial fractions, and then just to save time, I'll give you the solution to this. So the solution is P is equal to n beta e to the beta t, all divided by beta beta minus delta n, and it's shown in the notes, plus n delta e to the beta t. Okay, so that's the solution when you solve this by integration. Now when we plot the solution curves to this, and I'm going to give you the MATLAB program. So this is from program A to B. So we will have a look at the programs later. Then we have what's called a carrying capacity of the lake, which is given by beta over delta. So the birth rate divided by the death rate gives us something called the carrying capacity. We're going to change the color now to get the solution curves. We'll use the wheel and we'll use red. Okay, so if we start with a population, say down here, then the population will rise exponentially and reach this ceiling, this carrying capacity. And if we were to start above, then the solution curve would come down, and again we go to the carrying capacity. Okay, so on the left of the axis we have our time, and this the y-axis gives the population. And I'll explain more about this when we look at the MATLAB program for plotting these solution curves. So that completes the first video for separable differential equations.